Now going to turn to a type of top-down nanofabrication that incorporates self-assembly, which is the use of self-assembly to make masks for then etching nanostructures by more traditional methods. The example I'm going to focus on is the use of block copolymers. So let me tell you what a copolymer is. Let's begin by discussing some polymers. So let's draw here CH2, CH, CH2, CH, and then on all of these guys, let's add a benzene ring. This is polystyrene. Another type of polymer is polybutadiene, and this looks like carbons connected by alternating single and double bonds like this. So there are hydrogens attached to each of these carbons. The difference between the two is that at room temperature, this is a brittle, glassy polymer, whereas polybutadiene is a flexible, rubbery polymer. And so if the appropriate length of a rubbery and a glassy polymer are linked together in what's called a diblock copolymer, and the temperature adjusted appropriately, then the rubbery polymers will tend to associate in one phase and the glassy polymers into another, forming as shown here, for example, a material with stripes of a particular phase. Now it's also possible by controlling the conditions to form spherical aggregates of polymer, and they have a remarkably well-controlled distribution. So what I'm showing you here is the etching process. So the idea is to then place on the surface of the sample to be etched the diblock copolymer annealed so as to produce the appropriate phases, which I'm going to show here by little spheres, and then to either etch away or to stain the material. So in the case that you etch away, this is shown on B on the slide on the left, you can then expose the surface with the polymer on it, and as a result, eventually etch a surface that looks something like this. Alternately, you can stain the sample so as to make them metallic and achieve a reversal in contrast with the appropriate etches. So here are some electron micrographs. On the left are the domains after the removal, in this case of polybutadiene, leaving spheres of polymethyl methacrylate behind. And then after this surface is etched, B shows the little posts of, in this case, silicon nitride after reactive ion etching. Cylindrical domains can be made with the appropriate deposition of polymer, and in C, the cylindrical domains have been marked by staining with a heavy metal stain, osmium, and the cylindrical patterns transferred to the underlying silicon nitride surface after the appropriate etching steps. Clearly, the disadvantage of this type of masking is that very complex organized structures like computer processors are hard to make. On the other hand, for making, for example, small magnetic structures for hard drives, this is a really wonderful technique, and one that beats the resolution of any type of lithography by a large amount, since masks can be made with features down to a very few nanometers using these techniques.